Hello my schoolers, welcome to my school YouTube channel. My name is Manuel and today we'll be tackling JAMB past questions for chemistry in the year 2000. Please don't go anywhere, stick around and we'll be right back. You're welcome back to my school YouTube channel. In this video, we'll be tackling past questions from 1 to 25. Now, let's start with question 1. The first question says, a mixture of iodine and sulfur crystals can be separated by treatment with what? How do we separate the mixture of iodine and sulfur crystals? Don't forget that iodine is a sublimable substance, okay? It can undergo sublimation, and sulfur crystals are here. How do we separate the two of them in the mixture? The first option says you should treat the mixture of iodine and sulfur with water so that you can filter off sulfur. Option B, carbon 4 sulfide to filter off iodine, ethanoic acid to filter off sulfur, methanol to filter off iodine. Among these options now, this cannot be because none of this is going to dissolve in water. Okay, so even though water is a universal solvent, it's not going to dissolve iodine. Iodine will not dissolve in it and sulfur will not dissolve in it. So we need to look for a suitable solvent, okay, that either of these can dissolve in it, then we filter off and then we get the other one. So carbon 4 sulfide will dissolve sulfur, okay, because we have iodine and sulfur crystals in the mixture. So when you add carbon 4 sulfide into this, the sulfur crystals will dissolve into this and then you can filter. So once you filter off that, you'll be able to have the sulfur crystals dissolved in the carbon 4 sulfide, and then that will go through the filter paper into the container, and then you have your iodine as your residue. So in that case, we'll be able to have this sulfur crystal separated and then we have this separated. So the right option is option B, carbon 4 sulfide to filter off iodine. Now let's move on to question number 2. Sieving is a technique used to separate mixture containing solid particles off. Is it small sizes, large sizes, different sizes, and the same sizes? Actually, sieving is a technique of separation of mixtures that is based on relative sizes, different sizes of the particles that make up that substance that is supposed to be separated, okay? So if they are having the same sizes, then there's no point to sieve. If the particles have just large sizes, okay, without having variation in their sizes, there's no point sieving. If they have just small sizes, there's no point. But the reason why we need to sieve is because we have different, particle sizes, okay, of the substance that make up the mixture. So in this case now, it's a technique that is employed when you want to separate solid particles of different sizes. Not small sizes, not large sizes, the same sizes. We have different sizes that's present. So the right option here is option C, different sizes. Let's move on to question number 3. Which of the following compounds is composed of aluminum, silicon, oxygen, and hydrogen? Among these options, which one has these elements, okay, that make up this particular compound? There's something we call elimination method, okay? You look at the options, which one cannot be? At least there will be one or two that you are sure of that it cannot be this. For instance, limestone, we know that is calcium carbonate, okay? So if you write that calcium carbonate, CaCO3, this is what the formula of calcium carbonate is. There's no calcium among this, so definitely it cannot be this, okay? Then let's look at it. Maybe you are not familiar with the Epsom salt, you are not familiar with clay, and then urea, but urea, you know, at least from your urine, so you know it's nitrogenous, okay, waste. So nitrogen. So because there's no nitrogen here among all of this one, so it cannot be this. But the formula, just for the record, that is NH2CO NH2. That is what the formula for your urea is. So nitrogen definitely is not, even though, and carbon is not also here. So there's no aluminum here, so it cannot be this. So let's move on to Epsom salt. Epsom salt is actually magnesium sulfate, okay? That is Epsom salt. So magnesium sulfate, MgSO4. We don't have magnesium as any of this one, so this one cannot be. There's no point wasting time. Your clay. Clay, of course, is a type of soil, okay? You know, we say we have loamy soil and so on and so forth. Soil, and then we have sand in it. So definitely, and you know from your, basic chemistry that the sand usually is silicon dioxide, SiO2. So that should give you an indication that what silicon will definitely be part of this. Okay, oxygen will be part of this. Okay, aluminum is part. This is actually aluminum silicon. That is what we call clay, aluminum silicon. So it has the formula as Al2SiO5. Okay, then we can have molecules of water present in it. Okay, that's why we have the H here, because it is clay. Most time it is moist. Okay, so we have aluminum, we have silicon, we have oxygen here. Some case, maybe if you check some textbook can write it as Al2S, okay, Al2O3, okay, dot SiO2. Your SiO2 is your sand, okay, SiO2. So of course O3O2, that gives you O5. So this is the compound. So we have aluminum, we have silicon, we have oxygen, and we have hydrogen present in this. So the correct answer is option C. Clay has all of these elements made up of the compound. Question number 4. 50 cm cube of carbon 2 oxide was exploded with 150 cm cube of air containing 20% oxygen by volume. Which of the reactants was in excess? Which of the reactants was in excess? So there's a reaction between carbon 2 oxide, that is your CO, and then with air. Usually when we say a substance is reacting with air, we are referring to oxygen, because oxygen actually supports combustion. Okay, so even though we have about 21% of oxygen present in atmospheric air, because it is the part that supports combustion. So when you say in chemistry a substance is reacting with air or in air, we are talking about oxygen. Okay, so there's a reaction between carbon 2 oxide and oxygen, okay, to give us usually carbon 4 oxide, carbon dioxide. Let's go over to the board and we can see the reaction that takes place here. Okay, carbon monoxide reacting with oxygen to produce carbon 4 oxide. So the first thing you need to do, you have to balance up this equation. Okay, we have 2 here and then we have 2 here. So if you check, we have 2 carbon here, we have 2 carbon here, 2 moles of carbon here, molecules. Then 2 times this oxygen, that's 2 times 2 plus 2, that's 4. So 4 all together moles of oxygen on the left hand side, then 2 times this to 4. So the equation is balanced now. So the ratio is ratio 2 is to what? Is to 1 molecule. Ratio 2 is to 1 molecule to give 2 moles of CO2. But our business is not with this carbon 4 oxide. It is with between this, because they said we should know which one. The question says which of the reactant was in excess. These 2 are the reactants, okay? They are reacted together to produce. So the relationship is between 2 is to 1. So that means it is a ratio 2 is to 1. But we were told that 50 cm cube of carbon 2 oxide was exploded. So 50 cm cube will mean, so if here were 50 cm cube, okay, what is going to be this according to Avogadro's law of proportion? So we have ratio 2 is to 1, then 50 cm cube will be what? Of course, if here is ratio 2 is to 1, if here is 50, so that means half of this will be what this is. So this will be 25 cm cube. If we have ratio 2 is to 1 is the combining ratio, then if here were 50 cm cube from the question, then that means this should be what? 25 cm cube. Then we were told again that this was exploded with 150 cm cube of air containing 20% oxygen by volume. 20% oxygen by volume. So we should calculate 20% oxygen by volume, and the volume was what? 150 cm cube of air. So of 150 cm cube of air. So we can calculate what 20 cm cube, that's 20, that will be 20% is 20 over 100 times 150 50 over 1. So we have 0 cancels 0 here. We have this 0 cancels this 0. So we have 2 times 15. So that is 30 cm cube. Now, what was available was actually 30 cm cube. Okay, because we were told that it was bombarded with 150 cm cube containing 20% of the total volume. So, which means that 20% of the total volume of the oxygen was actually 30 cm cube. So, if 30 cm cube was what was made available, okay, but from the stoichiometry, from the equation, now the ratio shows that it is ratio 2:1, which means that 50 to 25. So, which means 25 cm cube actually took part in the reaction. The total volume of oxygen that was available was 30, but only 25 took part in the reaction. So, which means we have a remnant of 30, residual of 30 minus 25, we have 5 cm cube. So, which means we have 5 cm cube unused. Okay, we have 25 took part in the reaction. 30 was made available, was provided to what? To partake in the reaction. But by the time they combined together, it was only 25 that was used. So we have 30 cm out of the 30, 25 was. So it shows that this was actually in excess. So it was oxygen that was in excess, not carbon 2 oxide and not carbon 4 oxide. Of course, this is the product. Okay, so let's go back to the board and look at the option now. Okay, option 1, option A, we have carbon 2 oxide. We have carbon 4 oxide. Of course, it is not carbon 4 oxide. Carbon 4 oxide, no. Oxygen and nitrogen. Nitrogen is not even in the equation. Okay, so we have reaction is between CO plus O2. Okay, to find CO2. So this is not the answer. Okay, this is not carbon 4 oxide. This is the product, so it is not a reactant. Okay, oxygen out of 30 cm cube that was provided, only 25 cm cube was used based on the stoichiometry, okay, the combining volume ratio. So we have oxygen having excess of what? 5 cm cube. So it is not option D, but option C happens to be the reactant that was in excess, because we have 5 cm cube still left behind of that. So the correct answer is option C for this question. Now, question number 5. How many moles of hydrochloric acid, HCl, will be required to react with potassium heptazodichromate 6 to produce 3 moles of chlorine? 3 moles of chlorine. So the reaction actually is between potassium heptazodichromate 6 and HCl. So what this question or the examiner requires of you is just to write a balanced equation, chemical equation of the reaction between this and this, okay? So that you have the product, then you balance it, so you know the number of moles of HCl that will be required. So let's move over to the board now. This reaction, this is your potassium heptazodichromate 6, K2Cl2O7. When it reacts with HCl, you are going to have KCl, one of the potassium here. We have here K here, Cl will be there. Then we have chromate reacting with this chlorine, KCl3, because this is actually having oxidation state of +3. So this Cl will be 3. Then we have chlorine also be formed, and then we have H2O here, water molecule will also be formed. So these are the products here, and these are the reactants. So we are going to balance up this equation now. So we have 2 potassium here, 2 moles of potassium here. So let's write 2 here to balance this. So we have 2 now. So balancing that, we have this is 2 for carbon, and this is potassium is 2, but chlorine is 2 here. Okay, and then okay, let's see, chlorine is 2 here, chlorine is 3 here, but how many chromates do we have here? Chromium, we have chromium is 1, chromium is 2 here. Okay, so let's have 2 added up here also to balance up the chromate. And then let's see, oxygen is 7 actually. Then let's see, oxygen is 1 here, so let's add 7 here. Okay, let's add 7 here. So we have added 7 here. So I think everything about this now is okay on this side. Potassium is 2 here, potassium is 2, chromium, okay, is 2 here, it is 2 here, oxygen is 7 here, oxygen is 7 here. So now let's balance up the rest. So to balance up this now, let's count the other elements that combined with these other ones we balanced up, so that we can balance it on this side. So chlorine here is 2, Chlorine is 2 here. Chlorine is, this is 2 times 3, that's 6. Chlorine is 6 here, that's 2 plus 6. Then chlorine is 2 here, that's 6 plus 2. And then we have 2 plus 6, that's 8 plus 2, that is 10. So that is 10. So we have 10 chlorine on this side, okay, then to balance up this. But let's also look at how many of this hydrogen do we have here. We have, this is 7 times 2, we have 14 hydrogen on this side. So to make it easier, since it is only hydrogen that we have here, so you can multiply this to get the number of moles of hydrogen we have on this side. 7 times 2, that is 14. So if we have 14 moles of hydrogen on this side and we have just 1 here, so I think it's easier to put 14 here. So we have 14 moles of hydrogen here, but this has already altered the number of moles of chlorine, okay, atom that we have here. So but every other thing is balanced. Potassium is balanced, it's the same we have here. Chromium is balanced here, oxygen is balanced here. So hydrogen here is also balanced, but the only issue we have now is with the chlorine. So we already know that chlorine here is now 14. So let's try to balance up this since we have chlorine left out here. So chlorine here is 2 plus chlorine here is 2 times 3, that's 6. Then this is 2 here, okay, actually. So this is, let's not write this. This plus this, that's 8. So 8 is here, and then we are going to 14. So 14 minus 8, that's going to give us 6. Okay, so that means this one, the whole of this should be 6. But we have 2 already here. So that means if we bring in 3 here, 3 times 2 will give us 6. So I think the equation is balanced now. So you can check up again. Potassium is 2. Potassium is 2 here. Chromium is 2 here. Chromium is 2 here. Oxygen is 7 here. Oxygen is 7 here. Fine. So hydrogen is 14 here. Hydrogen is 7 times 2, that's 14. Then chlorine is 14 here. Then chlorine is, that's 2 plus 2 times 3, that's 6. 6 plus 2, that's 8. Then 3 times 2, that's 6. 8 plus 6 gives us 14. So that equation is balanced. Okay. So which means that we have 14 moles of HCl here to react up to give that. So let's go back to the screen and let's see the options we have there. How many moles of HCl? So our concern is with HCl, okay? So we have option A is 14, option B is 12, C is 11, option D is 10. For among these options now, from what we just saw now, you discover that HCl actually has 14 moles, okay? That guy. So the correct answer is option A, 14 moles. Question number 6 now. The ratio of the initial to final pressure of a given mass of gas is ratio 1 is to 1.5. Calculate the final volume of the gas if the initial volume was 300 cm3 at the same temperature, which means at constant temperature. So it is Boyle's law that actually stated the relationship between volume and pressure. This is between pressure and volume at constant temperature. And what does it state? It states that the volume of a given mass of gas is inversely proportional to the pressure, provided temperature remains constant. So which means as pressure is increasing, volume will decrease, or as volume is increasing, pressure will decrease. So it is inversely proportional. So let's go to the board now. The relationship is between pressure, okay, and volume. So they are inversely proportional to each other. So which means that V will be equal to K over P. So which means PV is equal to K constant. So which means P1 V1 is equal to P2 V2. From the question, we're told that P1 ratio 1, P1 and P2 are in ratio 1 is to 5. 1 is to 1.5. So which means initial pressure is 1. And then the final pressure is 1.5. It's given in the question. And then we're told that V1, okay, is actually 300 cm3. So we're asked to find the final volume, that is V2, if the initial volume was 300 cm3. So looking at this relationship, we can just put in these parameters now that we have values into this, and then we solve for V2. So P1 from this will be 1 times V1 is 300. That will be equal to P2 is 1.5. then times V2, that's unknown, okay? So we have here as V2. So making V2 the subject of the relation, we have 1 times 300 divided by 1.5. Of course, you have your calculator on your computer or on your system that you're giving, so you can just punch this and get your answer. But since I don't have one, I'm going to solve this by heart. 1 times 300, that is 300. This is divided by 1.5. So that will be 300. I change this to, that's divided by 1.5 is the same thing as 3 over 2. So that will be 300 multiplied by, it becomes, this goes up, this becomes 2 over 3. So 3 here, 1, 3 in 300, that is 100. So we have 2 times 100. So which is equal to 200 cm cube. So this is the volume. So you can look at the relationship. As pressure increases from 1 to 1.5, volume should decrease because they are inversely proportional. So volume is 300, so the value should be lesser, which is what? To 200. So we have 300 for initial volume. The final that we have to find, V2, is 200 cm cube. Now let's go over to the board and see the screen, and let's look at the options that we have. Option A is 120. 200, 450, 750. So among these, the correct answer from what we got now is option B, which is 200 cm cube. Question number 7 now. The partial pressure of oxygen in a sample of air is 452 millimeter mercury partial pressure, okay? And the total pressure is 780 millimeter mercury. What is the mole fraction of oxygen? Don't forget that according to the law of partial pressure, we said that the total pressure is equal to the partial pressure of each of the gases that make up the mixture of that gases. So which is P subscript T is always equals to PA plus PB plus PC, as many gases that combine to form that mixture. But in this case now, I want to calculate just the mole fraction of one of the gases that make up the mixture of gas, okay, of the air. Okay, so let's move on to the board now. So to solve this, we'll represent the mole fraction with X, okay? X mole, we'll just write that XM fraction of oxygen, because we're asked to calculate the mole fraction of oxygen. So the mole fraction of oxygen will just be partial pressure of the gas. Which gas are we looking at? That is oxygen. Okay, divided by the total pressure. Total pressure of what? Of the air, of air sample. Okay, so that will be, in other words, we can represent it as partial pressure of oxygen over total pressure of that. So from the question, it's just a direct question. We're given that the partial pressure of oxygen is 452 millimeter mercury, 452 millimeter mercury, okay? So dividing that by the total pressure was given as 780 millimeter mercury, 780 millimeter mercury. Of course, by the time you cancel out that and you divide this using your calculator, you are going to have 0.579. If you punch that on your calculator, you are going to have the 0.579. So let's go back to the screen and look at our options. Okay, from the answer we got now, 0.579 is in option B. So this is the correct answer. So the mole fraction of oxygen in the mixture of air, the whole of the air, is actually 0.579. Question number 8. The fundamental difference between the three states of matter is the what? Remember that the three states of matter are solid, liquid, and gaseous state. Okay, so what is the major difference between them? That's what the examiner wishes to find out from us. The option A says shape of their particles. Is that really difference between them? Shape of their particles. You agree that solids actually have shapes, okay, because of the way the particles are compacted together. But we would have gone for shape, okay, but because something actually made the shape, gave rise to the shape, okay, it is what? The way the particles are compacted together, is actually what gives the shape. Okay, so some are loosely bound, some are, you know, starkly bound together. Okay, and it allows for free movement of what, of the molecules in what. So shape of their particles is not a fundamental difference. Okay, even though we know that the liquid, we always assume the shape of the container, the solid has a definite shape, but that is not a fundamental difference. Okay, we have option B says number of particles in each state. Number of particles in each state. No, that is not a fundamental difference between them, because number of particles actually varies from time to time, but you know, there are other factors that actually can influence this. Okay, if we have a candle that is solid, if you apply it to it, it's going to melt to liquid. So this number of particles in each state does not really, you know, it's not a major difference, it's not a fundamental difference between the three of them, because the particles of solid, of liquid, we have the particles of gaseous substances, you know, moving freely and colliding. We have that of liquid also moving freely. So option C says shape of the container they occupy. That is not a fundamental difference between them. But look at option D, degree of movement of their particles. What makes a solid what it is because the particles are, you know, are solidly, are compactly, you know, stacked together, are closely, you know, packed together. Okay, which is different from the way the molecules of, or the particles of liquids are, and that of gaseous substances are. Okay, because of the movement of their particles. So usually, you know that solids, the particles don't move. Okay, what they only express is vibration. When you throw up a substance, it lands. The vibration, there's going to be vibration between the particles that make up that solids. Okay, for liquid also we have, because the particles or the molecules that make up the liquid are not closely, they are still closely packed together, but not as that of solid. Okay, you have them also moving. There's free movement, there's movement. Okay, but that is greater than that of solid. Then the gaseous substances, gaseous, in fact, because they are not held together like the liquid and the solid. Okay, the particles of the gaseous substances have the liberty, freedom to move as they wish. They collide with themselves and then with the walls of the container in which they are put. So among these options now, the fundamental difference between the three states of matter is the degree of movement of their particles. We talk about entropy for gases. Okay, their level of what? Their level of disorderliness. Okay, inside of that. So the correct answer is option D, degree of movement of their particles. Now let's move on to question number 9. Which of the following statements is correct about the periodic table? Option A, elements in the same period have the same number of valency of electron. Is that correct? Elements in the same period have the same number of valency electron. That is wrong. Elements in the same period have the same number of shells. Okay, it is elements in the same group that have the same number of valence electron. They have the same number of electrons in their outermost shell. So option A is not true, it's not correct about the periodic table. Option B, the valence electron of the elements in the same period increase progressively across the period. Is that correct? The valence electron of the elements in the same period increase progressively across the period. Yes, that is correct, because the valence electron is the number of electrons we have in the outermost shell, okay, of the atom of an element. Okay, it says that as you move across the period, okay, it increases. Yes, it increases. Why? Because the number of the atomic number actually increases as you move across the periodic table, across the period, okay, of a periodic table. So as you are moving across from left to right, the atomic number increases, and as the atomic number is increasing, the number of valence electron in the outermost shell of the element will also be increasing progressively. So option B is correct. Let's look at option C. Elements in the same group have the same number of electron shell. No. Elements in the same group have the same number of valence electron, not electron shell. Electron shell, number of shell is for elements in the same period. Okay, so this is not true. The non-metallic properties of the elements tend to decrease across the period. No, non-metallic properties of the elements tend to increase. As you move across each period, it increases, not decreases. So the correct answer here is option B. The valence electron of the elements in the same period increases progressively across the period. Option B is the correct answer. Do you know you can actually take practice questions with our simulated JAMB CBT past questions? All you need to do is click on the link in the description below that takes you to the Myschool website, where you have opportunity to download the Myschool mobile app for your Androids and Myschool software for your laptops and computers. Please go ahead and start practicing. Now let's go to question number 10. The electron configuration of X22, that's 2+, that's the valency of 2+ ion, is what? Now, to attempt this question, you need to know first that we have what 22 is. That is what? That is our atomic number, okay? That is number of proton. And we are talking about what? Electron configuration. Electron, not proton. Electron. So, the way electrons are arranged for this element. Now, if we didn't have this +2, it would have just been 22. So, we will say that this would have been a neutral atom, meaning that the number of proton would have been equal to the number of electron, okay? So, it would have been 22. So, all we need to do is we begin to add up this superscript that we have here. That's what denotes the electron. Then, when it gives us 22, the one that gives us 22, then we pick, okay, among them. But in this case, we have +2 here. So, which means that this is positive 2. So, which means that among the three subatomic particles of an atom, that is proton, neutron, and electron, the one that is positively charged is actually the proton. So, having +2 here means that proton is what is in charge. So, what does it mean? It means this element X has given out. Remember, if you look at one of the video lessons we talked about when we're dealing with atomic structure, okay, part 1, 2, and 3, if you look at it very well, we said that when metals give out electron, donate electron, they become positively charged, okay? So any ion, any atom of an element that gives out electrons becomes positively charged, while non-metals accept electrons to become negatively charged. So this means this is a metal actually that has given out 2 electrons. That's why it is what? Positive, 2 positive. Now it has given out 2 electrons to become positively charged. Now the question is, if the number of protons were 22, what will be the number of electrons? Remember, this is not a neutral atom. If it were a neutral atom, number of protons would have been equal to number of electrons. But in this case now, proton has given out 2 electrons, has been given out by this method. So if 2 electrons have been given out, so which means electron will no longer have the same number with proton, because it has been shortened by 2. So 2 electrons has been given out. So if 2 electrons are given out instead of 22, so which means we will have 20 electrons left. So this element has 22 proton now and 20 electrons, because 2 electrons has been given out already out of this 22, so to have 20. So we have 22 proton and 22 electron. We are talking about electron configuration. So we just begin to add up the number of electrons here as the superscript, okay, to know which one gives us 20. So we are looking at one that has what? 20 now, 20 electrons. In other words, if there's going to be loss of electrons, the 4s, okay, will definitely lose out its electron first before the d, because we know in the orbitals, okay, electrons, there is what? Energy levels, okay? So it is 4s that loses electrons first before we get to the 3d, okay? So let's look at what we have. If you look at this, 2 plus 2, don't forget we are counting 20 electrons now, because 2 electrons have been given up. 2 plus 2 is 4 plus 6, that's 10. 10 plus 2, that's 12. 12 plus 6, that's 18. 18 plus 2, that's 20. Plus 2, that is 22. No, this is not correct, because this is 22. This is saying we have 22 electrons. Meanwhile, it is 20 electrons we have, because 2 has been lost. This is 2 plus 2 plus 6, that's 10. 10 plus 2, that's 12 plus 6, that's 18. 18 plus 2, that's 20 plus 1, 21. So this is not correct. So let's go to option C. 2 plus 2 is 4, 4 plus 6, that's 10, 10 plus 2, that's 12, 12 plus 6, that is 18. So 18 is not correct. Let's move to option D. 2 plus 2 is 4, 4 plus 6 is 10, 10 plus 2 is 12, 12 plus 6 is 18, 18 plus 2 is 20. 20 electrons are present here, so which means option D is the correct answer. I believe you are enjoying this content. If yes, please don't forget to click the like button, hit on the subscribe button, and finally tap the notification bell to keep you informed once we upload our next video. Let's go to question number 11 now. Which of the following types of bonding does not involve the formation of new substance? Formation of new substance. Okay, we have metallic, we have covalent, we have coordinate, we have electrovalent. Like I said earlier on, that there's something we call elimination method. You look at among the options which one cannot be. Okay, we're talking about the formation of new substance. Okay, we know that electrovalent bonding has to deal with transfer of electrons from metals to non-metals. Okay, and then once the metal is reacting with a non-metal, we have a new product which is electrovalent compound. Okay, so that is a new product, a new substance is formed here. For this, coordinate and covalent are actually, covalent bonding. Coordinate covalent bonding, or we call it dative bonding, is a type where the two lone pair of electrons that is shared among the participating molecules are actually donated by only one among the two. Okay, while this one now, covalent bonding, also involves sharing of electrons, but the electrons that will be shared between the two, each of them of the participating molecules will do what? Will donate, the other one donates, and then they share together. These two involve sharing of electrons, and then a new substance will be formed. But for metallic bond, even though we have delocalized ions involving among the metallic ions that are present there, but those bonds are just there. Okay, the metals are just bonded together. We have those delocalized ions in between them, but they don't form the bond actually. Okay, so the bonding is actually the metal still remains. For instance, sodium ion will still remain sodium ion. Okay, even after the bonding has taken place. So we just refer to it's just a mere bond, metallic bond, because there's no new substance that is formed. The sodium ion remains sodium ion even after the bonding has taken place. But this one, you have chlorine reacting with another chlorine atom to give us chlorine molecule. So a new substance is formed. Here, ammonia can react with nitrogen with hydrogen ion with a proton to be formed ammonium ion. That's a new substance formed. Sodium can react with chlorine to form sodium chloride. Those are new substances. But for this now, the following types of bonding does not involve the formation of this. So among all of these four, this involves formation of new substance, this involves formation of new substance, this involves, but this is the only one that does not involve formation of any substance. So the correct answer is option A, metallic. Let's move on to question number 12. The knowledge of half-life can be used to what? Create an element, detect an element, split an element, irradiate an element. The question is, what is half-life? Half-life has to do with the number of times, okay, a substance is split into half, okay, undergoes decay, okay, to split into half. That is what half-life is. The time it's going to take. It could be years, it could be months, it could be, hours, depending. That element, the nucleus of an element begins to split into half, okay. That is what we call the half-life. Now, the first option says create an element. Half-life does not help to create an element. What creates an element is radioactivity, okay. Radioactive decay will help to create an element. You discover that you have the nucleus of a different element entirely. So radioactive, but half-life will not do that. Detecting an element, yes, it should, because half-life of each element or substance are actually specific. Each element have their specific values for half-life. Okay, so let's assume uranium, let's say it has 1620 years before it decays. Okay, it is specific for it. No other element has that here. So we can be able to say, okay, an element X has 1620 years for what? For half-life to decay. Before it decays into half of that. Okay, we say, okay, which element has that? Okay, it is uranium. Okay, we can be able to say, okay, it is element. So we can detect an element. So the knowledge of half-life can help us detect an element. Option C says split an element. No, half-life will not help us split an element. Okay, it is either we have nuclear fusion or fission. Okay, if we have nuclear fusion, a bigger nucleus of element will split, okay, to form several smaller ones. Okay, that will help us, not half-life. And this one irradiates an element. So among these options now, the correct answer is option B. The knowledge of half-life can be used to detect an element because the half-life of each element are actually specific. Question number 13. The shapes of carbon dioxide, CO2, H2O, and CH4, that is methane, respectively are. We have bent, we have linear, we have tetrahedral, and so on and so forth. Now, if you know that CO2 has a shape that is linear, then this is how to solve questions smartly. You don't need to waste much time. Just go through the option. CO2 is known to have a linear shape. I will tell you why. Okay, just look at the options. The option that has, because they say respectively, so which means the first one should be for CO2, bent should be for this, and why the third one should be for this. Among these three options now, the ones that have linear as CO2 is only option C. So don't waste your time. Just click option C and then you move on to the next question. Solving the question in the shortest time and solving correctly. But I'm going to explain what happens. Now, in the video lessons, we talked about atomic structure. Okay, you can go through it again. You can subscribe to that. Atomic structure, we dealt so much on how you can know what the shapes of molecules are, what the shapes of solids are. Okay, now CO2, there's something about shapes. What is responsible for the shape of molecules? Electron repulsion. That is one of the major things. We talk about VSEPR, valence shell electron pair repulsion. Okay, that is a theory. The theory states that the first one says that there's electron repulsion. There's a repulsion between electrons, and the other one is talking about the bonding electron and then the lone pair of electrons. So if you listen to that video, you will do more. So because for the sake of this and for the sake of time, there is a repulsion between the molecules of oxygen. This is CO2. We have a central atom here, which is carbon. Okay, we have bonded here oxygen on this side because there are two bonded on this side. Now, the bonded electron here, because there's the electron for this carbon now, they are the same. So they begin to repulse. There's a repulsion. They repel. Okay, and this repulsion now begins to make these oxygen atoms to separate far apart. And as they separate far apart from this carbon atom, they form an angle 180 degree, of course, between this and this. So there is a linear, shape of this. So the angle here is 180 degrees. So the electron repulsion between the oxygen atom and this carbon atom, this central carbon atom, is what actually gives rise to the shape of this CO2 to be linear. Remember what I said about the shape of molecules? It has to do with electron repulsion. Okay, look at H2O again. H2O, we have two atoms of hydrogen. Hydrogen is here, another hydrogen is here, and then we have oxygen at this side. Just one. Okay, so one here, one here. Oxygen has two bonds, hydrogen has one and one. It should have been this way. Okay, but there is a lone pair of electron for this oxygen here. Okay, that causes the repulsion. Okay, but there's a bond between oxygen and hydrogen here. So these tend to bend this. The attraction here, because of the lone pair of electron for this central atom, is not as this, because this carbon does not have any lone pair of electron. Okay, there's pair of electrons that we have here, bonded electrons here. Okay, so this one here is not more. So it will now bend this such that this will no longer be this way. It now forms something like this, and then this also will be this. So this will now give us a bent shape of the molecule of water. And for CH4, that's your methane. There's a central carbon atom here. That's the central atom, carbon, and then we have 4 hydrogen bonded round about it. Hydrogen, and hydrogen here. okay, because they all are equally, and then they are what? Connected to this, and they repel the carbon atom here. So they are bonded together in the same angle around this carbon atom. So this one forms a tetrahedral shape. So we can say that CO2 has a linear shape, water has a bent shape, and then tetrahedral shape is the shape of methane. So look at the options here. CO2, because it's respectively, so CO2 should be linear, bent, and tetrahedral. Linear, bent, and tetrahedral. So option C is the correct answer. Linear, bent, and tetrahedral. Question number 14. The distance between the nuclei of chlorine atoms in a chlorine molecule is 0.194 mm. The atomic radius of the chlorine atom is what? Don't forget that two nucleus make us a nuclei, okay? So two atoms of chlorine combining together to form a chlorine molecule. Let's move on to the board and let's see how that is. This is a chlorine atom. This is another chlorine atom, okay? Bonded together, of course. This is the nucleus at the center for this. This is the nucleus for at the center for this, okay? Chlorine atom, chlorine atom. The distance between here to this point, okay, that's where that bonds the chlorine together. You say the distance between the nuclei of chlorine atoms in a chlorine molecule is that. So 0.1. So that means different from here to here. Distance from here to here is actually 0.194 mm as given from the question. So the question says the atomic radius of chlorine. So which means that if you separate the two, the distance from here to here is what they ask us to find, or the distance from here to here. So one of this atomic radius from here to here is what. So if from here to here is 0.194 and the distances are equal because they are the same atom, okay, so that means we just divide this by 2. 0.194 divided by 2. So we have that will be 0.0 here, that will be 7. That will be 9, that's 18, yeah, when the 1 in this, that's 14, okay, that's 7. So 0. So the radius, so which means from here to here is 0.097, from here to here is 0.097. Okay, so if you add the two together, you should have the distance from here to here. So the correct answer is 0.097. Let's move on to the screen now. So among the options for what we got now, option A happens to be the correct answer, 0.097 mm. Question number 15. The noble gas argon is used for what? Electric arc welding, welding brass, underwater welding, steel welding. Elimination method, you can decide to look which one cannot be, do you think cannot be. Now, we talk about welding brass, okay? We talk about, this is supposed to be an alloy, okay? And this steel is also an alloy. We have carbon, and that's okay. So, welding, they are all welding, kinds of welding, but noble gases, argon. Noble gases, don't forget, they are group O elements, okay, in the periodic table. And one thing they are known for is their inertness, okay, unreactivity, chemically unreactive. So they have a low reactivity, especially this argon. Argon is considered suitable, okay, for a particular kind of welding because of its low level of reactivity, okay, with metal because they are inert. Apart from that, non-flammable, okay, the flame, no matter how you increase the pressure of argon flame, argon gas, this argon, no matter how you increase the pressure or the temperature, it does not, it is non-flammable, okay? It doesn't form, and then it is non-toxic. So because of those three characteristics, non-toxic, non-flammable, okay, and then low level of reactivity with metals, argon is suitable and is used usually for electric arc welding. Electric arc welding. So among these, option A is the correct answer for this option. Noble gas argon is used for electric arc welding. Question number 16. A side effect of soft water is that, remember what is soft water? We have soft water, we have hard water. We also treated that in one of our video lessons when we talked about water. Okay, a side effect of soft water is that the difference between soft water and hard water is that soft water has little or no minerals that are dissolved, calcium, magnesium, salts dissolved in the water. Okay, so that is the difference. Now, the effect of that, apart from other disadvantages or effect of salt water, could be that because it does not have those minerals present in them, once they see lead, they react with lead. Okay, because they want to drag along lead present in them. So if you have salt water flowing through a lead pipe, okay, maybe water running through and it's salt water, once it is because the pipe is made up of lead, there's level of reactivity, so it will drag along, it will react with the lead, okay, in the pipe and drag along the pipe and begins to, form, what's it called now, layers, okay, of that in the pipe that is made up of the lead substance. So in other words, a side effect of salt water is that option A says it gives offensive taste. No, of course it gives, because it does not have those minerals there, it could have a flat taste anyway. But if it is a good water, it should not have taste, it should be tasteless. Okay, so it's not option A. Option B, excess calcium is precipitated. No, if it were hard water, we say excess calcium can be precipitated. Okay, because calcium ion would have been present in hard water. Option C, it attacks lead contained in the pipes. Yes, I said that earlier on. That is one. The soft water are sensitive, are reactive with lead. So any pipe that is made of lead, you should not run soft water through it. If you run soft water through it, it's going to drag along the lead ions that are present as it moves, and then it's going to attack the lead that is contained. And option D says it encourages the growth of bacteria. No, not at all. It attacks lead contained in pipes. So the correct answer is option C. It attacks lead contained in pipes. Let's move on to question number 17. Water molecule can be ligands, especially when they are bonded to what? What are ligands? That's the question you should ask. Ligands are molecules, okay, or ions that are bonded together to a metallic central atom. There's a central atom, the atom that bonds to other molecules or ions. So that is what we call substance. And water molecule can act as ligands, okay? Substances or molecules, of course, that's water molecule that are bonded, okay, to a central metal atom. We say that is so. Water molecule can be ligands, especially when they are bonded to. We have alkaline earth metals, transition metals, group 7 elements. Of course, it cannot be group 7 elements because group 7 elements are halogens. Okay, so we said ligands will form what? Will be molecules that are bonded to central metal atom. Okay, so you cannot be group 7 because group. So we eliminate group option D. So now we have metals, option A, option B, option C. So it's between these three. Now these are metals, so it could be any of these three. But now the question is, among these three, there's a special kind of metals that their characteristics or properties is they have formation of ions, complex ion formation. We have a variable oxidation states. They have catalytic properties. They have magnetic properties. Okay, and that is the transition metals. So if water molecules form, ligands, okay, bond to metals, okay, central metal atoms, we refer to them as aqua, A-Q-U-A, okay, aqua, okay. So they bond with transition metals. It could be copper, it could be iron, okay. We have them, bonded to those central metals. So the type of metals that has that characteristics of forming complex ion, okay, with ligands, okay, is what we refer to as transition metals. So because they have partially filled 3D orbital shells. So water molecule can be ligands, especially when they are bonded to not alkaline earth metal, that's group 2 elements, not alkaline metals, that's group 1 element, but transition metals. So the correct answer is option C, transition metal, because they have tendency to form complex ion with the ligands. Let's go to question number 18 now. The air pollutant unknown in nature is what? Which air pollutant? They are all air pollutants. Which one does not occur naturally from nature? Okay. Option A says NO, that's nitrogen 2 oxide, that's nitrogen monoxide. This actually you can get it in nature. Okay, it's in the atmosphere. We can get it in the atmosphere. Option B is CO, that's carbon monoxide. You can get that from monoxide or carbon dioxide. You can get that from exhaust, from pipe of cars, generator sets. The smoke that come, of course, is a poisonous gas, but you can get it in nature. Option C is, of course, we can have it as organic. Option C, HCHO. This is called formaldehyde, or what we call formalin. It has different names that you can call. You can call it formalin. You can call it formaldehyde. Okay, formaldehyde is a type of hydrocarbon. Okay, so because it's hydrocarbon, so it means it is organic. Okay, so you can find it in nature. But DDT is used for some years as insecticides. Okay, DDT is just an abbreviation for the name diphenyl trichloroethane. Okay, diphenyl trichloroethane, DDT, but you can't find it in nature. It is not organic, so it is produced. Okay, it is a synthetic, kind of product. Okay, that is used in the treatment of maybe insecticides and to use as so it is actually a pollutant, but does not occur in nature. Okay, it is not natural, so it is inorganic, so it is DDT. So among these options now, the air pollutant unknown in nature that cannot be found in nature is actually option D, DDT. Question number 19. 1.0 dm cube of distilled water was used to wash 2.0 gram of a precipitate of silver chloride. That means silver and chlorine ion actually form that silver chloride. If the solubility product of silver chloride is 2.0 times 10 raised to the power minus 10 mole per dm to the power of 6, what quantity of silver was lost in the process? What quantity of silver? So silver ion, of course, was gotten from what? From silver chloride. Okay, so in this we're told that the solubility product of silver chloride is actually 2.0. So let's move to the board and see what we have. Okay, so solubility product of that, so which means we have silver chloride. Okay, gives us, if we dissociate that, we are going to have silver ion plus chloride ion. So what we have to find is to find the quantity of silver, okay, that was lost in the process. So you cannot find that without dissociating first. Okay, so when we dissociate that, we're given that the solubility product of silver chloride is 2.0. So we write this KSP. KSP stands for solubility product of this. Okay, is a constant of this silver chloride is 2.0 times 10 raised to power minus 10 mole dm to the power of 6. Okay, minus 6. Okay, that's what the solubility product constant was given to us. But let us say that, let the solubility of each of those silver and chlorine now, of solubility of silver and chlorine to be equal to, we can represent with letter X or letter D, whichever one you feel like, with letter D. Okay, so if we have that, so it means that the solubility product for constant for silver chloride should actually be the concentration of silver ion times the concentration of chloride ion. That's what we have. So by the time, don't forget that we have represented solubility of each of these with D. So which means KSP will be equal to, where we have this, we substitute to be D. That will be D times, it's also D, because they have the same number of moles. Okay, and the charges are just what is different. So we have 1 1, and that's so they can represent it. So we have D. So this will be KSP potassium. That's not potassium, that is solubility product for constant for silver chloride. So this will be D squared, that will be D squared. So don't forget that we're giving the solubility product constant for silver chloride to be 2.0. So we just represent that as 2.0 times 10 raised to power minus 10. So that will be equal to d squared. Of course, if you make d the solid of the relation, you transfer this becomes square root of 2.0 times 10 to the power of minus 10 equal to d. So d will be equal to, we find the square root of this, punch it on your calculator, we have 1.414 times 10 raised to the power minus 5. So which means that since d is this, so which means each of them, silver should be 1.414 times 10 raised to the power minus 5. Then chloride also, or chlorine will also be 1.414 times 10 raised to the power minus 5. So if you multiply the two together, we should be able to have 2.0 times 10 raised to the power. But we're asked only for what? For silver. We're asked that what quantity of silver was lost in the process. What quantity of silver was lost in the process? So with this, let's go to the screen now and see what option. So answer. Option A is that 2.029 times 10 to the power minus 3, 1.414 times 10. You have to be careful with this. This is the same thing as this, but you can see this is 10 to the power minus 3, while this is 10 to the power minus 5. From our answer, which is 10 to the power minus 5, not this. So the correct answer is option D, 1.414 times 10 to the power of minus 5 mole per dm cube. Option D is the correct answer. Question number 20. Hydration of ions in solution is associated with what? Hydration of ions in solution is associated with what? For us to have the ions being hydrated, okay, we are adding water. You hydrate, you add water to it. What happens? The hydration of ions in water, when they begin to hydrate, the ions in the solutions, when they begin to hydrate, that is an exothermic reaction, okay? Because once that happens, once ions are being hydrated in solution, what happens? There will be loss of heat from the system into the what? To environment, okay? Once that happens, that means heat begins to what? To get liberated. So we look at option A, says absorption of heat. No, it will be absorption of heat if it is endothermic. If heat is absorbed into the system, okay, we say that that is endothermic. For this, reduction of heat, heat is not reduced. Conduction of heat, no, it's not going to conduct heat, okay, but liberation of heat, heat will be liberated because it is an exothermic reaction. And an exothermic reaction, heat is released, is liberated, okay, is given off, okay, from the system into the surrounding environment. So hydration of ions in solution is associated usually with liberation of heat. So which means option D is the correct answer. If you have any questions to ask, please feel free to ask your questions by clicking on the link in the description below that takes you to the Myschool website, where you have opportunity to ask your questions and answers or solutions will be provided within the short period of time. Now let's move on to question number 21. HCl reacts with H2O to form hydronium ion plus chloride ion, okay, in the reaction above. Cl minus is the what? What is Cl minus? Now, the reaction is between HCl. Of course, don't forget HCl is an acid. And acids usually, when they dissolve in water, what happens? They liberate a proton or they liberate hydrogen ion, okay? So this is dissolved or dissociated in this water now to form hydronium ion. So what happens once this HCl is associated here in this atom? The hydrogen will be what? Will be donated, will be liberated, will be given off, okay, will be formed, and then leaving behind, look at it, this is H2O, okay? The hydrogen is added to this, or the proton is added to this H2O to form H3O. So leaving behind this chlorine. So this chlorine is left behind, becomes a chloride ion. You can see that here. So because the hydrogen has been taken, proton has been donated to this water, it has been dissociated in this water to form H3O positive, okay, hydronium ion. We have what? Chloride ion will be left behind. So that chloride ion that is left behind is called a conjugate base. Conjugate base are usually formed from an acid, okay? When an acid liberates or donates a proton or hydrogen ion once dissociated in water, what is left behind is what is called a conjugate base, okay? So from the options, conjugate acid, no, conjugate base and base. So it is conjugate base. So option C is the correct answer here. That conjugate base is what? Cl minus, because it was from what? HCl, from an acid. And once a proton is donated or is dissociated in water, is given off or hydrogen ion, a proton is hydrogen ion, we form what is left behind is a conjugate base. So the correct answer here is conjugate base, option C. Do you think you have a better or an easier solution to some of the questions that have been solved? Please, you can share what solutions you have. You can do that by going to the comment section and then you indicate the question you wish to answer and then the correct or a better or simpler solution to solving those questions. Question number 22. In which order are the following salts sensitive to light? In which order are the following salts sensitive to light? Okay, of course, if you see we have greater than, so which means from highest to the lowest. Okay, and what we have silver iodide, silver chloride, silver bromide. So those are majorly the three substances that we have here, and this is what we call silver halide. Okay, silver halides. Halides are from halogens, group 7 elements. So when silver reacts with group 7 elements, we form silver halide. So it now depends on the whether it is silver chloride with chlorine, silver iodide with iodine, silver bromide with bromine. Okay, so in what order do these salts are they sensitive to light? Now, silver bromide and silver chloride, both of them actually are used in photographic film, making, okay, because of their sensitivity to light, both of them. But in this case now, they want us to tell us in what order do those salts are these salts. They are all salts, okay, actually are they sensitive to light? They have generally silver halides have a property of sensitivity to light. So in what order? So the easiest way to solve this is it is in the order as you go down the group in the periodic table, the order of reactivity. That is what is going to be. So first, we have fluorine, we have chlorine, we have bromine, we have iodine, okay, for the group 7 elements. But we don't have fluorine here, okay. The reaction from chlorine, bromine, and iodine. So in order of reactivity, it is usually chlorine is more reactive than bromine, and bromine is more reactive than iodine. So also we can say silver chloride is greater than silver bromide and greater than silver iodide. Okay, so let's look at the options. We have silver chloride, iodide to chlorine. No, this is a decreasing order. We have silver chloride is greater than iodide. No, this is not it. Silver bromide, silver chloride. No, silver chloride greater than silver bromide and greater than silver iodide. Yes, this is more sensitive to light than this. This is more sensitive in light than this to this. So option D is the correct answer to this question. Question number 23 now. The pOH of a solution of 0.25 mole per dm cube of hydrochloric acid is what? Okay, pOH actually measures the level of alkalinity, okay, of a substance, and then we have pH also. pH measures the level of acidity, okay, of a particular substance or acid. So we want to calculate now the pOH now is that. So, and we know that, let's move over to the board. We know that pH usually is negative logarithm of hydrogen ion concentration, but we are not dealing with this now. We are dealing with pOH, okay. pOH now, the level of alkalinity now is also negative logarithm, but in place of this hydrogen we have what? OH minus, okay. So this is what we're going to contend with. pOH is negative logarithm of hydroxyl ion, so that will be negative logarithm of, we have that to be 0.25, we're given from the question, okay, that's equals to minus logarithm of, that's 2.5 times 10 raised to power minus 1. So with the aid of your calculator, you can punch this. We have this negative value will be here. We have logarithm of this. By the time you punch this of 2.5 times 10 to the power minus 1, we have 13.40. Of course, negative 13.4 0. So by the time you multiply this, negative cancels negative, you have a positive here, that is 13.40. So of course it should not be beyond 14 because 14 is the highest value that we should have, okay, on the pH scale, okay, 14. So 13.40 should be our answer. So let's move on to the screen now and see what we have. Option A, we have 12.40. Option B, we have 13.40. Option C, 14.4 and 14. Of course, elimination method, C and D cannot be the answer because the value of the pH scale ranges from 0 to 14. So anything beyond that so it cannot be C. This is 14.4, that's gone beyond 14. C and D cannot be, so it's between A and what? And B. So, and from what we just did now on the board, option B happens to be the correct answer, 13.40. Question number 24. MnO4 minus, okay, minus 1 minus, okay, plus 8 moles of hydrogen ion, there's an acid here actually, okay, reacting with that, plus Y gives us Mn2 plus D. So the question says Y in the equation above represents what? So what, in essence, what the examiner expects of you is to find the number of electrons that will be on the left hand side. So all we need to do is we balance what we have on the left hand side, number of electrons, with what we have on the right hand side. So let's move to the board now to see what to do. So the number of ions that we have here, we have electrons here. This is minus, of course, that's minus 1. Okay, so minus 1 here, plus, this is plus 1 here. So you multiply this 8 by 1. There was actually 1 here. So 1 times minus 1, we still have minus 1. Okay, so 8 times plus 1, we have plus 8 on this side. Okay, then plus what? Plus Y. So where we have this, that will be equal to, this is what? Plus 2. 1 times 2, that's plus 2. Of course, water 4 times, no charge, 0. So that's 0. So let's not, okay, we can add that plus 0. Okay, so let's simplify this now. We have minus 1 plus 8, that's plus 7. 7 plus Y will be equal to plus 2 plus 0, that's plus 2. Okay, that's 2. So we have 7 plus Y is equal to 2. So positive Y will be equal to, we have 2 here, and of course, we move this to the other side, it becomes what? It becomes minus 7, okay? So that is positive Y will be equal to 2 minus 7 gives us minus what? 5. Minus 5. So which means what we have here is just 5. So we have 5 what? Electrons, of course, to be here. So what we have here for the place of Y is there is electrons. So 5 electrons is what we have. So let's move to the screen now and see what we have. Of course, it is minus because it is electrons, okay? So we just have the E minus here. So we have it as minus. So let's move to the screen and let's see. We have option here. This is 2 electrons, 3 electrons, 5 electrons, and 7 electrons. So the correct answer is option C, 5 electrons. That's why it is minus 5. So we have 5 electrons at that point. So option C happens to be the correct answer. Question number 25 now. Half moles of zinc ion plus electron gives half moles of zinc sulfur, okay? That's solid, okay? Zinc solid. Now in the reaction above, calculate the quantity of electricity required to discharge zinc. This is what? Electrolysis, okay? What amount of electricity, okay? Because electrolysis has to do with the amount, okay, of electric current, electricity that enables, okay, a particular ion to be discharged, okay, to form metal, okay. So we want to calculate now the quantity of the electricity that is required to what? Discharge zinc, bearing in mind that 1 Faraday is equal to 96,500 coulomb. There's a relationship in between the mass of the substance and then the quantity of electricity, because that is what the Faraday's first law of electricity states, looking at the relationship between the mass of the substance being directly proportional to the quantity of electricity or current that is passing through at that particular point in time. But you also bear in mind that 1 Faraday, 1 mole usually is equal to the number of moles is always equal to number of electrons equals to number of Faraday, okay? Number of Faraday. And we're told that 1 farad is 96,500 coulomb. Let's move to the board so that we do justice to that. So it means that 1 mole, okay, should be equal to 1 farad, okay, because we have, but in this case now we have 1 electron. Of course, definitely is going to be by number of electrons. So we have, if it is 1 electron, it will be 1 times 1, so which is 1 electron. But in this case now we have 2 electrons there, because zinc ion from the screen, we have 2 electrons. That is the ideal thing that it should be. So it should have been 1 mole should be equal to 2 electrons or 2 farad, because we have 2 electrons of zinc ion. So that's 2, so which is equal to 2 times 1 farad, we're told, is given as 96,500. So 1 mole is supposed to give us 2 times 96,500 coulomb. That is what it should be with the equation of zinc 2 plus 2 electrons, okay, to give us zinc solid. That's what it should be, okay, because 2 electrons actually will be, zinc is going to gain 2 electrons to become what? To become zinc ion. So we have 1 mole should be equal to 2 times 96,500. If it were aluminium, Al3+, it would have been 3 times 96,500. So in other words, we are saying 1 mole is equal to 2 multiplied by 96,500 coulomb. But the question says, calculate the quantity of electricity that is required to discharge zinc. So you look at how many moles from the equation that was given. We're given that half zinc, okay? So which means half mole of zinc, not 1 mole now. This is the situation when it is 1 mole of zinc ion. But from the question, we're told that it should be half zinc. So half zinc, half moles of zinc, okay, implies that when it was 1 mole of zinc, it was 2 times 96,500. Now that it is half mole, that is 0.5 mole of zinc, what is going to be the quantity of electricity that is just the relationship, and that's easy as that. 1 mole of zinc would have given us 2 electrons, that's 2 times 96,500 coulomb. That is the quantity of electricity that would have discharged that zinc. But the number of moles is reduced from 1 now to half zinc, half mole from the equation, 0.5 mole. What will it be? So by the time you cross multiply, what do we have? 1 mole time, that's going to be x, will be equal to 0.5 multiplied by 2 multiplied by 96,500. Okay, so by the time you multiply that together, what we are going to have, so of course we can do this even without calculator. 0.5 is the same thing as 1/2, right? So we have times 2 times what? 96,500. So 2 here cancels 2 here, so we are left with 96,500, which is 1 farad. So from the options, we have it in standard form. So let's change this to standard form. This is the point was actually here, so it becomes 1, 2, 3, and 4. It has to be, decimal point has to be between the first and the second number to change standard for 1, 2, 3, 4. So that is 9.65. You can add 0 to it, times 10 raised to power. We are going from right to left, so that is positive. Positive, we moved it 4 times, so 4 coulomb. So which means that 9.650 times 10 to the power 4 coulomb amount of electricity will actually be required to discharge half mole of zinc in that point. Let's go to the screen now and see what we have is our option. Option A says 0.965 times 10 to the power 4. This is to the power 4, okay? 10 to the power 4 coulomb, okay? That is not it. 4.2820. From the question we solved now from the board, what we have is 9.650 times 10 to the power of 4c. So option C happens to be the correct answer. 9.650 times 10 to power for option C. I believe you enjoyed this content. If yes, please don't forget to click the like button, hit on the subscribe button, and finally tap the notification bell to keep you informed once we upload our next video. Please subscribe.